Okay, everybody, let's have a look at the handout here. So we're going to look at the problems on this. So the first one we're going to see here, we have this rectangular box with dimensions 8, 10, and 12. What fraction of the box's volume is not within 1 unit of any of the box's faces? So, okay, so we have a diagram of our box. It looks something like this here, okay? Now, let's look at the dimension. If we're not sure what to do about this, let's look at each of the dimensions individually. So imagine we put a little tape here, a tape measure along the side here, so it's labeled from 0 to 10, right, like this. Now, if we don't want to be within a unit of any of the box's faces here, we just look at just that. If we don't want to be within a 1 unit of the faces, which are at 0 and 10, where will we be? We should be somewhere between 1 and 9, right? Because we want to have that 1-inch buffer space on each end. So that means we know it's going to be somewhere between 1 and 9 along this dimension here, right? But by the same token, we can do this for every single thing here, because we can do the same thing by putting a 12 here, so this is between 1 and 11, and for 8 we can say this is between 1 and 7 here. So by doing this, we actually, if you try to, draw this into our box, we actually see that we have a smaller box, like this, on the inside here. We've got a smaller box, and again, I apologize, ladies and gentlemen, my sketches aren't that great. We have a smaller box here on the inside, something like this here. Now, in this situation, this smaller box, well, we know its dimensions here, because we know that from here, from 1 to 9, we're just lopping off 1 from each end. So this is going to be 8. Here we have 1 to 11, so that's 10. We're lopping off 1 to each side. 1 to each side here. Again, we have 6 here. So basically, what fraction of the volume of the box is basically this blue volume over the entire black volume here. So this is going to be 6 times 8 times 10, all over 8 times 10 times 12, and we see how very fortunately the 8s drop out, the 10s drop out, the 6 and the 12 leave a 2 behind, leaving us with a very convenient 1/2. Okay? Let's move on to number 4. So this is an old Armo question, a problem from the national contest here. So you have Bridget, who has 2 boxes here. She places a rectangular prism on the floor, and she's putting a stack on top of this. So you can just imagine this as 2 books, right? You want to put 2 books on the table, and you want to create the smallest possible surface area. Now, intuitively, in order to do that, that means we want to cover up as much things as possible. So we just focus on the 4, 6, 8 here. Since we're not painting anything that's touching the floor, we're not moving the boxes here. It makes sense to put the biggest possible face on the floor. So that means our stack is going to look something like this. We want the 6 and the 8 on the bottom like this here. So right now, our optimal case is going to look like this. We want the 6 and 8 on the floor and the 4 on top here, okay? Now, we have to put the 2, 3, and 5 on top of this as well. So in this situation here, if we do the same thing, if this were on the floor, we can imagine there's a floor on top of the box, and we can do the same thing here. By doing this, we're going to stick the 2, 3, 5 on top, so we want the smallest face on the bottom here. So again, 2, 3, 5, we're going to put the 3 and 5 on the bottom here, so it looks something like this. Again, I apologize, ladies and gentlemen, this is not drawn to scale, this is really awful, but you get the picture here. 3, and then we have 2 up here, okay? It's 2 up like that, okay? So our box, our stack looks something like this here, okay? So now it's just a matter of finding the surface area. Well, the surface area is pretty easy to calculate here. Let's take a look at this. So on the outside here, we have, so for the lower box, well, let's see. It's going to be, note that we can unwrap the strip of lateral faces here, so it becomes a big rectangle here. And we can use our formula from 4. The lateral area is the perimeter of the base times the height. So it's going to be double 8 plus 6 times 4, which is 2 times 14 times 4. And that will yield you a total of 8 plus 4, 8 times, so let's see. We will do this as 28 times 4, which is 112. Okay. That seems good so far. Now we want to look at the top. We still have to add the top face. So this is the sides, and then we have to add the top. Now the top is the 8 times 6, but the bottom of the upper box covers up some portion of it, so we have to subtract 5 times 3. So there's going to be 48 minus 15, and that yields you 33. Okay, now we can look at the upper box. The upper box, there's only 5 faces that are visible. The bottom face, the 6 faces on the bottom here, it's covered up. So it's just a matter of adding all of it up. Again, we can do the same thing. We can dilute the lateral face here. So it's 2 times 5 plus 3 times 2, plus the top face, which is 5 times 3 here. So this is, in this case, it's 2 times 8 times 2 plus 15. 2 times 8 is 16 plus 2, 16 times 2 is 32. So 32 plus 15 yields you 47 here. So therefore, we have 112 for the bottom face, plus 33, plus 47 here, and that yields you, so in this case, let's see, 33 plus 47, that is 30 plus 40, that's, let's see, that's, this looks like 80 here plus 112 is 192. So this is our minimum, okay? Our third situation, now we have a pan like this here. So let's take a look at this. So right now our pan looks like this here. We're going to place cubes in it one at a time until the cubes are going to be submerged. So one of the first things you probably learn, probably one of the first labs that you do, is that you may recall you having sort of a glass cylinder and you put a little rock inside and you watch as the water goes up a little bit and you use that to calculate the volume of the rock. So we're going to be using displacement here. When we put a cube into the container, it's going to increase the height. The height of the water is going to increase here. Now, it starts at 3 here. If we want the cubes to be submerged, what do we want here? If the cubes are submerged, since the cubes are side length 4, we want the height of the water to go above 4. So we want the height to be greater than 4 here, right? So that would be really important here. As long as the height of the water is greater than 4, we're good to go. As you can see, after we place some number of cubes in here, we want the height of the water to be at least 4, because then it's going to cover the top of the cubes. Otherwise, it's going to only go up to the side of the cubes and not cover it up. So now we have to figure out what's going on here. First off, we note that in this situation here, the water has no this pan has no cubes in it right now. It's just water. So we just calculate the volume of this. So the volume of this is just simply 20 times 25 times 3. Okay? So we seem to have this sort of thing here, 20 times 25 times 3 here, like that. And we have, this is the volume of the water here, okay? Now, I realize I've forgotten a problem that I mentioned. You need to make sure that 15 is the height, okay? So 20 by 25 is the bottom here. And now, we're going to add cubes. We don't know how many cubes they're going to be. We're going to add n of the cubes, okay? So we're going to add n cubes. Now, it's going to be n cubes of this, and each cube has volume of, well, let's see, the cubes are side length 4 centimeters, so it's going to be n times 4 cubed. Over here, we want the height to be great, so we want the height to be at least 4. So that means this here is going to be the water plus the cubes, and we want this to be strictly greater than what would happen. We want the height to be greater than 4, which means we want 20 times 25 times 4. So right now we have ourselves this nice little inequality here. We can put this together. So let's see. This is here. We can put this together. So I can write this as 64n is greater than, well, let's see. I have 20 times 25 times 4 over here and 20 times 25 times 3. If I subtract that from both sides, the 20 times 25 is going to remain there. And how many of them? We have 4 copies of that. Now we have 3 copies here. So we subtract that and we're left with 20 times 25 here. Okay? So therefore, now we have 64n is greater than 20 times 25. So therefore, n is greater than 20 times 25 over 64. And we just have to figure out what that looks like. Well, luckily here, there's a 4 and 20, leaving me a 5 behind, and the 4 down here, leaving me a 16. So this is 125 over 16. So that means n is greater than 125 over 16. Now, if you use a calculator, you can figure out what this is approximately here. So let's see, 16 times 6 is 96. 16 times 7, I think 16 times 7 is 100 and, let's see. So 16 times 7 here, sorry about that, I had to do this myself. So that, I believe, is 112, and we see that we'll go over if we do that. So that means this is going to be, n is going to be greater than 7, and in this case, 13/16 here, right? So that means n should be 8. So there should be 8 cubes in the box.